So for the first part, what we have been given is that this is the question about the rate of change. So first part is that there is a model that is W is equals to 20 to the power minus KT. Now, initially, since the given variable, a given function has certain unknown like K, they have given us a way to find out K. So they have given that when after 50 hours, the weight was 10 grams. So basically when T is 50, the W was 10 gram. So using that, we can find out the K values. Plug W as 10 and T as 50, and you solve for K, that comes to be 0.014. So that's your first part. So now we have got like finite model, which is like W is 20 e to the power negative 0.014t. Our next part is to then use this model to either use technology or manually substitute the values. So like plug T as 0 here, then plug T as 24 here, then plug T as 1 week, but 1 week won't be you will not put 1, you will put like 7 times 24 because T is in hours. So that's just that one thing we have to be careful, and you'll get the values. The next part is how long will it take for the weight to reach to 1 gram? So once again, this is a normal function question. So you just like equate the weight function to 1. Now, if you solve using technology, if you solve using logs, you'll get this as answer. So you can just plot this graph. You can plot this graph and see where they're intersecting. And so you'll see that they're intersecting at 213. Or if you don't want to do like the plotting way, you could just do as negative 0. E to the power negative 0.014t equals to 1 over 20. So negative 0.014t equals to ln of 1 over 20. And so you get the value of t straight away from here, which will be 203.98. Now coming back to our rate of change question now, which will be, now they're saying that, okay, find the rate of radioactive decay at t equals to 100 hours. Now when you say rate of change is nothing but the derivative of W with respect to time. So dW by dt is gonna be 20 e to the power negative kt times negative k. So this is the rate of change formula. Now, what we do is plug t value here, you'll get the exact rate of change at that 100 hours. So we have got the k value already. So just if I plug 20 e to the power negative k times, let's say 100, I'm assuming that you're putting k as 0.014 and times 0.014. So this will give us the rate of change or rate of decay when it is 100 hours. Similarly, plug T as 1000 here, you will get the rate of change of radioactive substance weight after 1000 hours. So rate of change is simply the derivative, or you just find out the derivative and plug in the x coordinates, or it's like a normal slope formula. But a couple of questions that are asked in IB, they link up with understanding about the slope, understanding about the rate of change. That gets a little confusing with the related rates. But the related rates and rate of change, we are two different concepts. In related rates, we link up with two different quantities, while in rate of change, we have just simple one quantity being differentiated with respect to the variable that has been given in the function. Now, last part is show that dW by dt is proportional to the weight of the substance remaining. Now, dW by dt, so dW by dt is nothing but, if I do that, it will be 20 e to the power negative kt times negative k. Chain rule, so e to the power fx times f dash x. Now, as we can see simply here, dW by dt is, I can say is, this is nothing but W. This is same as W formula. So if I can put here negative K times W, and you can clearly see that dW by dt here is proportional to W if I remove the constant. So this is how you kind of do the basic questions on rate of change.